All right, I think we'll get started. Welcome to review session for exam number 3. You know how this works by now, so I'm here to answer any questions you have, so shoot. Go ahead.
You talk about the important parts of galvanic conversion that we have to know.
Sure. So the important parts of galvanic corrosion that you should know are things like which metal is more noble than the other and how do you tell. I will give you the noble metal series in the notes to the exam, so just know how to use it. And so what type of metals like to corrode, anodic or cathodic metals? Cathodic metals, right? So things that want to be cathodes will oxidize. So that's an important point, so you can look up different metals on that table and tell which one is going to corrode or not. Also, if I give you two metals, say copper and silver, how do you tell? And I say, which way is the reaction going to go? How do you tell from the E0 cell? Well, E0 cell. How do you tell? So if I give you E0 cell, how do you tell if that's going to happen or not? Go ahead. If it's greater than 0, right? If E cell is greater than 0, then what happens? Then delta G is negative NF E0 cell. And so if E0 cell is greater than 0, that means delta G is going to be less than 0. And so this is going to be thermodynamically favorable. So I could give you an E0 cell that's negative, and I'll say, is this thermodynamically favorable or not? And you would say, no, it's not, because of the sign of delta G. So those are the important points about galvanic corrosion, being able to work your way around which metal is going to corrode, which is not, the sign of delta G based on E0 cell, things like that. Yes? The anode does. So the anode oxidizes, right? So an anode is something like Zn goes to Zn 2 plus 2 E minus. So this is an anodic reaction, or it's oxidation. And so the most corrosion that we know about is anodic corrosion, and so we're going to turn metal, zinc 0, into zinc ions, and then the ions will float away and the metal corrodes, right? Cathodic reaction is something like silver plus 1 electron goes to Ag0. This is a cathodic reaction, and it's reduction. And in this case, we're making metal, right? We're making silver 0, so there's no corrosion going on there, right? We're making metal in that case, and that's good. Other things that you should know about corrosion, just in general, what's a good oxide coating? You know, aluminum oxide versus iron oxide versus chrome oxide. Those are the big ones that we talked about. So having an idea of what's a good coating and what's not a good coating is important. Being able to work your way around Courbet diagrams, that's an important part of corrosion. What phase is going to form where and under what conditions. Yeah?
What other metals don't have a good coating besides iron?
Let's see. So, would you suppose that zinc has a good coating on it?
Yeah.
Why do you say yes? Yeah, so when you galvanize something, what do you do though? You coat something else with zinc, right? And then the zinc slowly goes away and iron is left over. So, in general, zinc corrodes more than other metals, and so zinc probably doesn't have a great coating on it, even though we use it as a coating in galvanization, which is a little different. But iron is the most important one. Or I could give you a metal. I could say molybdenum oxide is a porous coating. It lets water through, it lets oxygen through. Do you think it would be passive coating or non-passive coating. So if I tell you some properties of the coating, you should be able to tell me whether it would be a corrosion-resistant coating or not.
And passive means it's good, right?
Passive means it stops corrosion, right? Yeah, so anything that's a passive coating like aluminum oxide or chrome oxide, those stop corrosions. They passivate the surface. Yeah,
Can you go over the Arrhenius equation and
Sure.
linearizing it for graphing?
yeah, that's a good idea. Okay, so what does the Arrhenius equation describe? What in relation to what? What's important about Arrhenius?
Relates rate with temperature.
Relates rate and temperature, right? So anytime you hear rate and temperature, anytime you hear Arrhenius, you need to be thinking rate equals R0, some constant, sometimes this is called A. You see this as A. Times the exponential of negative EA over RT. So this is called the Arrhenius expression, or the Arrhenius equation. And this rate is the rate that we've been talking about all along in kinetics, right? So rate equals K. What order reaction is this?
0.
0. That's a good answer, nice and loud. Rate equals K, concentration of M times the concentration of N. What order is this? Second, good, right? We just add up the exponents, and you know how you know about that. How do these equations depend on temperature? We don't know, right? It's at a constant temperature. So we have these rate equations to tell us what order the reaction is, and we know about plotting these things. But this is at a constant temperature, where the rate is first order, second order, 0th order, things like that. So Arrhenius relates rate to temperature. So we would have some sort of rate, we would have a bunch of temperatures, and as the temperature increases, say here's 298, here's 400, here's 700, is the rate going to increase or decrease? Increase, right? Rate usually increases with temperature, and so the rate's going to go from 6 to 7 to 25. What are the units on rate? Moles per second. So rate equals moles per liter per second, or molar per second. How the concentration changes is a function of time. That's a rate. How many moles are used per volume per time. Okay, so how this all relates to temperature. Oops. So, what's the plot for an Arrhenius expression? How do we plot? If we want to know what's going on with the Arrhenius equation, what plot do we make? Anyone know it just off the top of their head? One over T ln rate. So how do we get to that? To linearize this equation, what we'll do is we'll take the log of both sides, so we have ln rate equals ln of this stuff, and log A times B is log of A plus log of B, so this is ln A plus log of an exponential is itself, so it's going to be minus EA over RT. So this is called the linearized form of the Arrhenius equation. Does anyone not know how to linearize the Arrhenius equation? Very important, because I could perhaps even give you a different form of this equation on the exam. You would have to linearize it. So figuring out, okay, how do I get rid of that exponential? What do I do with this? And so this is a linear form of the Arrhenius equation, and it tells us that we plot y, ln rate. What's ln of A? Constant. Right? And then x equals 1 over t, right here. And then this is the slope. So we have y is mx plus b. And so, which direction is this line going to go? As I increase temperature, which direction am I moving here? Where's high temperature and which low temperature on the x-axis? Go ahead, tell me. It's going to go like this. High temperature, right? 1 over T, so this is high temperature. High rate, right? And an ln rate is still a high, ln of a high number is still a high number. So here is high rate, high temperature. Here's low rate, low temperature. And the slope is negative EA over R. Negative slope, right? EA is going to be positive or negative? Always positive. What are the units on activation energy? Go ahead. Great. Joules per mole. Yeah, that's it. So we have the Arrhenius expression that tells us how the rate varies as a function of temperature. We can linearize it, and then just like we plotted for first order, second order, third order, we linearize the Arrhenius expression because we want to get a straight line where we can figure out what the activation energy is. And so, is activation energy a thermodynamic or a kinetic quantity?